In case you feel that I'm not audible, there is issue with network connectivity, kindly inform me. All right. Okay, so uh, just inform me, all right? We'll continue with the previous lecture regarding the transport layer. We started with the transport layer. We saw what transport layer is, what is its functions. We briefly did the function. We briefly did the protocols that are covered within it. And then after that, we studied about multiplexing and demultiplexing in the previous class. Then we saw what UDP is, connection less service. And also, we saw the UDP segment structure. In our today's class, we will start with the reliable data transfer. Okay, so basically what is reliable data transfer? What is reliability here? We want to ensure that if I am saying something to you, okay, you have received that. So how do I ensure that what I have said, you have received it? I message you, I broadcast a message like, guys, do you hear me? Like for example, just now, Ramanand, do you hear me? Do you hear me? Okay, good. So exactly this is the same thing that the reliable data transfer does. When it sends something, okay, it waits for the acknowledgement of the receiver to see whether it has received or not. When the receiver sends back an acknowledgement, yes, I have received it, it means it's a reliable data transfer. As compared to the previous one which we did in UDP, we said it's not reliable, but it's used for multimedia applications in which you just keep on saying, like you are listening to a lecture on TV. Okay, you cannot respond back to it. You are just on the receiving end. Okay, you are just on the receiving end. So in that case, you have no no capability in which you can reply back and say to them that yes, I have received or not. This is what reliability here is. Now we know TCP actually implements this reliable data transfer, but we are not as of now starting TCP. We'll first study what is reliability here. And to understand what this reliability is, we have two things here. One is the sender, another is the receiver. So we have a connection between the sender and the receiver. Sender sends the first packet, that is PKT0. Send is the instruction of sending this packet. So it sends it, and the receiver here, RCV, is receive packet 0. It received the packet 0. Now, until the receiver replies back and says that I have received the acknowledgement, it will not send the next packet. So sender is waiting here. During this time, sender is doing nothing. Then what is it doing? It is waiting for the acknowledgement. Receiver prepares an acknowledgement and sends back an acknowledgement. It's ACK 0, that is acknowledgement for packet number 0. It receives back acknowledgement 0, right? So after it has received this acknowledgement, the sender sends the next packet. So receiver receives the packet, sends the acknowledgement of that packet. Once the sender gets the acknowledgement of that packet, it prepares the next packet, and so on. This is how it will keep on going. This is how it will keep on going. Next, 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 next. But this situation is an ideal situation in which there is no loss. There is no loss. Compared to this, let's say this is a link with negligible loss like a fiber. Compared to this, if we see a link which is lossy link, the sender sends the packet here, packet 0. The receiver receives this packet 0 and sends an acknowledgement of packet 0. The sender gets this packet 0. Fine, this is okay till now. It is the same like we saw here. But now, next thing is sender sends the packet 1. It is lost. How it is lost? There are lots of, communication errors which we have discussed in our previous classes, and somehow this packet is not received by the receiver. In this case, what happens is the sender would wait for some time. Obviously, receiver cannot reply back. It cannot say, I have not received. Receiver cannot say that send again until it is sure that the sender has sent something. So what happens here is sender waits for some time. This certain amount of time here is known as timeout. That is this part. This is the time during which the sender expects that in case it was received by the receiver, the reply should have come back. However, we know it's lost. Plus some more time in case there was a delay in the packet. It considers that also. Delay from the receiver and also in sending the acknowledgement, it considers that also. After this is done, timeout, it now is sure that no, I am not getting any acknowledgement back. What it does, it prepares the next this packet once again. So the send packet that was sent here is within the buffer. It sends it again, and this time it was received. It sends the acknowledgement back, then the next packet, and so on. This is what happens in case we have a packet loss. There can be another situation as well, in which the sender sends the packet, the receiver receives the packet, sends the acknowledgement back. The sender sends back the packet and the receiver receives it. Till now it is fine, everything is okay. But instead of a packet getting lost, we have an acknowledgement getting lost. So acknowledgement loss means that the sender again would be waiting for a certain amount of time in which it expects the packet to be received. So we would have to wait for a certain timeout. So sender doesn't know whether it was the packet that was lost or whether it was the acknowledgement was the loss. It's waiting for the acknowledgement. Even if it's packet lost, even if it's acknowledgement lost, the sender would wait for that specific amount of time during which it expects that the receiver would send back the acknowledgement. Then what? It would send packet 1 again. But the receiver has already received this packet. So it detects that there is a duplicate packet. So it neglects the duplicate packet, but sends the acknowledgement here. That is this one. This time acknowledgement went far, okay, it was received by the sender, and this is how it would continue. This is in case of acknowledgement loss. The fourth condition, which we call as premature timeout or delayed acknowledgement, in the case first the sender sends it, receiver received it, sender sent the acknowledgement was received, but the next packet that was sent, okay, acknowledgement took time to come back. We had a premature timeout. It did not receive the reply by then. Then what happened? Acknowledgement was sent and the sender received the acknowledgement here. But before the acknowledgement was received, timeout had happened, what we call as premature timeout. Packet was sent once again here. This packet was sent again here once more. And the acknowledgement came after it. You can see here acknowledgement is reaching after this packet was sent. So what happens in this case? In this case, we have here a duplicate detected by the receiver. It sends the acknowledgement once again, that is here, as well as, you know, acknowledgement was received here. Whatever the sender prepared the next packet, so received a duplicate acknowledgement after the second one. Let me just clear it up. So let's see here. Since timeout happened here, next packet was sent here, but it received acknowledgement late. So receiving acknowledgement means that packet 1 was received successfully. It prepares the next packet and sends the next packet that we see here. But during this time, there was duplicate detected by receiver. It sent another acknowledgement for already received. The receiver sends this acknowledgement 1 and the sender receives this acknowledgement. But it has already received this acknowledgement where? Here. So what it does? It deletes this or ignores it because it knows that I have already received this thing. I have already received the packet. And this is how the reliable data transfer works. This is how we have the acknowledgements sent across. There are different protocols which we will come across to understand the operation of this. Among them, we have stop and wait and other protocols. We'll be going through each one back and selective repeat. Before I actually move on to these protocols that are mentioned here, let us have the overview of the next thing, that is TCP. That is Transmission Control Protocol. This is what we call as connection-oriented protocol. Connection-oriented transport layer protocol. So, before the sender and the receiver start the transmission, before actually the sender would send the actual data, the sender does a handshake with the other connection. What I mean by handshake here? Ramanand, can you hear me? Ramanand, I want to send a file to you. Can you take the file? Okay, the next thing I'm sending is the file. So this was an example. Ramanand, I'm not sending any file. So this was an example that before I actually was giving, I was going to give a file to Ramanand, I confirmed from Ramanand, are you okay? Are you able to receive the file? Are you active? Right? Do you have the capacity to receive? Is there any issue from your end you cannot receive? He said, no, I can receive. I'm fine with it. So I said, fine. Once I got his acknowledgement, I again told him, okay, next thing that I'll be sending you would be the actual file. This thing in which I first ask him, he replies back, then I confirm with him, This is known as three-way handshake. And exactly the similar thing happens in computer networks, in which the two end systems handshake with each other. Obviously, it's not a physical handshake. It's like sending off message packets across. And you tell each other that yes, we have received no, I'm able to communicate or not. And again, since TCP is a transport layer protocol, it is available in end systems. So we expect that no other intermediate devices like a switch, like a router would be able to understand this protocol. That's why the protocols of transport layer and above are known as end-to-end protocols. They are available in end systems. Likewise, TCP is a handshake between two end systems. So if I am connected with your laptop, okay, it means that no other intermediate device is able to understand this TCP protocol. And when I have sent something, Ramanand replied back to me, it is a full duplex transfer. TCP is a full duplex data transfer. We had bidirectional data flow in the same connection, and we could have the maximum transfer of the data using each segment, which we call as MSS. That is maximum segment size. And what is this maximum segment size? We will try to have this maximum segment size as per the lower layer protocols. So what I mean by lower layer protocols, remember MTU, data link layer as well as network layer. What was MTU? MTU was maximum transfer unit. That's how much was the maximum I could carry. Let's say 1500 bytes that we discussed. So likewise, we would have here MSS, that is the maximum segment size, how much we can have. And we will try to have it in such a way that we do not go beyond the maximum size that is prescribed by the lower layers, that is the network layer and the data link layer. If we get a large chunk of data from the application, we break it using segmentation at transport layer. If network layer gets a bigger segment size from transport layer, network layer does fragmentation. If data link layer gets a bigger chunk from the higher layer, it will do accordingly framing, so that we keep on the maximum this size, max MTU or MSS, that's the maximum segment size. Another thing that we have to understand in TCP, the first point that is given here, that it is a point-to-point protocol. One is the P2P that we understood, that we did in the physical connections. That was the topologies that we did. But in this case, we are not talking about the topologies, the physical one. We are talking about point-to-point connectivity. That is, if we want to have a connection-oriented transport, if we want to have TCP, it is between one sender and it is between one receiver. Which makes something interesting here, that we cannot have broadcasting in TCP. We cannot have multicasting in TCP. We'll expect only the one-to-one connection, one sender and one receiver. Why? Because of the reliable transfer, because of the handshake, because of the acknowledgements and so on, and retransmissions. We would want to have TCP as point-to-point. That's mentioned here as well. The next thing is that TCP is in-order delivery. What we mean by in-order delivery, let me draw a picture here. Let's say this is the sender, this is the receiver. In between we have some more devices, let's say a router. I'll connect these. If we first talk about UDP, okay, In UDP, the packets that are sent across can be unordered. So if this is my first packet, second packet, third packet, fourth packet, so this is 1, 2, 3, 4. This is how packets are generated, and this is how a receiver can receive. Now, since internet, we have, a lot of routers in between. There can be a packet, okay, let's say packet number 1, which has been directly sent across here through this link. But because of some issue within the router or within some of the link, second packet was sent through this route. Okay. And the third packet took direct route. What do we see here? This is the route for first packet. This is the route for second packet. Because of during that time there was some issue with the router, the link was busy, it took an alternate route. And this is the third router, third switch packet. In UDP, what happened here in that case, the packets that arrived here was first number 1. What was the next packet that came? Number 3. Then came number 2. Why? Because 3 came directly, it had a shorter route, so it took lesser time. 2 had a longer route, it took long time. So the delivery here, then let's say we got 4 and so on. So what do we see here? We see that the delivery of packets that was done here was not in sequence. And what do we mean by was not in sequence here? It means that it was unordered. It was unordered delivery. Why? Because 3 came before 2. And then what was to be done by the transport layer at the receiving end? It had to order them. It had to keep them one by one again back. Now coming to TCP here. TCP is providing us an ordered delivery of packets. Let's say this is the link. These are the routers and so on. Now in the case we have packets here. 1, 2, 3, 4, 5. This is 1. This is 2. This is 3. This is 4. And this is 5. Packet 1 takes a shorter route, let's say here, and reaches here. Packet 2 takes a bit of longer route and reaches here. Why? Because during that time maybe this path was busy. You have done this in routing. And then we have packet 3. Packet 3 takes again a shorter route. So in what order would we get packets here? That we need to see. So we will have these packets reaching here in an order in which we have, let's say, 1, 2, 3. This is what we explain in TCP, but UDP. But in case of TCP, in such a situation, we cannot accept packets which are out of order as of now. Then you'll see that we'll use different flow control protocols. We'll see how we can take some packets in chunks. As of now, keep this in mind that we would need in-order delivery of packets. Why? Because once one is sent across, we would expect that there is to be given acknowledgement of one. Let's see here. So what do we expect here? So this is the sender, this is the receiver. In this case, we expect if one packet is sent here, this is the first packet, send the acknowledgement back of one, the next packet is sent. Send the acknowledgement back of next packet. Then we have third packet. Send back the acknowledgement of third packet. So it is necessary that we get packets as 1, then 2, and then 3, and then so on. That we say we would need to have in order delivery for TCP. Okay, so we got some points here. The next thing is, which I just now mentioned, that it won't be possible in multicasting to have TCP. It won't be possible to have TCP in broadcasting. Simple, we can say 2 is a company, 3 is a crowd. It cannot be maintained within 3 acknowledgements and so on. There will be a lot of confusion. That's why we have TCP working in point-to-point protocol. MSS, we just mentioned it, MSS is the maximum amount of data that can be grabbed and placed in a segment. This is limited by the MSS. The common values that we see within MSS, the maximum is 1500. The lower one is 536, 512 bytes and so on. And again, I repeat, the segment size is often chosen such that you ensure that it is the MTU of network layer. You do not want to do IP fragmentation. That's why you will ensure that you keep the same size. Okay, let us now see the segment size, the segment structure of TCP. Remember the segment structure of UDP? It was pretty simple to remember. We had a payload and we had a small header. How much we said was the header size of UDP? 8 bytes. Okay. How much now do we have the header size of TCP? That is this green square that I have drawn. This is 20 bytes. So the difference of 12 bytes, we will see why do we have that many. Another thing that we saw in UDP, there were just 4 fields within the header, the source port and the destination port. We see them here as well. And there were 2 more things. One was length, another one was checksum. This part that we have down here, this is the application. This is simply what we get from the application. This is simply what we have the data. This is the message that we have to pass on. So what other things do we see other than the length and the checksum here? The port number remains the size of the port remains same. The source port number for 16-bit and the destination port number again 16-bit. Total that's mentioned here as 32. Then we have some things which is sequence number and acknowledgement number. What is the sequence number and acknowledgement? Both of them are 32-bit fields. This is 32-bit sequence number and 32-bit acknowledgement number. Actually, TCP sender and receiver implements reliable data transfer service using this sequence number and acknowledgement number. Like you give the sequence number to the packet that you are sending across and you expect an acknowledgement to that packet, so you would have an acknowledgement number for the packet. And to inform the sender and receiver about is this packet a data packet or is this packet actually an acknowledgement of it. For that, there are specific fields which are mentioned below here. So down there you can see application data. This is the data that is to be sent. Checksum, this is the same that we had in UDP, and this is the same internet checksum which we did while we were discussing error, when we discussed about when we discussed about a CRC, and there I mentioned that there is the third one which is internet checksum, the video of which you might have seen, and also I told you that this is implemented in transport layer. We saw it in UDP. Now we have similar to this here as well. The TCP field is of variable length, and this, why we say optional, this may be used, this can be to negotiate certain things between sender and receiver. An example of negotiation of MSS, that is the maximum segment size. Sender and receiver discuss between each other how much should be the maximum segment size. This is an example of that. Okay. And we have certain fields which are mentioned here. There's certain fields within the header. To start with, you can see this one is header length. This is a 4-bit field which informs how big is the header. Obviously, the size would change because there are some fields which are of variable length. So in order to inform how much is the header length, this field is used, which is of 4-bit. Then we have certain fields in which we have one of them as A, then we have RST. Let me see if, yeah. Okay. Like we have here A, this is known as acknowledgement bit, ACK bit. And what is this? Each, this C, E, U, A, P, R, S, F, this, each of them are of 1 bit each. So they basically they would denote just 0 and 1. It's a flag indicating whether it's on or off. So if we have A on as 1, we will expect that this segment that is being sent across is actually an acknowledgement for a packet. If the value that is carried inside the acknowledgement ACK field is valid, it indicates that it's an acknowledgement. We have RSF that is mentioned here as RST, SYN, FIN. These are basically for synchronization, reset, and this is what we know as connection setup and connection teardown. So connection management is done by these bits. Okay. Then we have this receive window which is mentioned here. It's a 16-bit receive window. That is here, 16-bit receive window. We'll understand this more when we do flow control. So this is used for flow control, in which we would have to inform the receiver, okay, whether it's willing to accept these many more and so on. Some other bits like we have here, that is CE, you can see here. This U here, this one. This U is an urgent bit. If it's, if it's valid, if it's on, it means that this packet is to be treated urgently, all right? It should have the minimum delay there. Another one that we have here is P, this one, okay? This P is basically PSH bit. It indicates that the receiver should pass the data to the upper layer immediately. Okay, So this is basically how the TCP segment structure looks like. And among this, we know this much, or let me say, this much is the header. This much is the header. Okay. Here it is giving an example of how we send and receive these sequence numbers. You have sent a sequence number of a packet, you expect an acknowledgement number of, it can be this packet or it can be the other packet. So an example of sequence numbers and acknowledgement numbers as given in Telnet. Okay, this is an example of Telnet. Telnet is RFC 854. Telnet runs on TCP basically. Okay. In this, if an acknowledgement is carried in the segment carrying the data, this is known as a piggyback. What do we see here? Host A and host B. Okay. A user types certain thing, a user types C here. C is sent across with the sequence number 42, acknowledgement 79, and data is C. Host acknowledges the receipt of C and echoes back C. It says, yes, I have received back C. And in this, it changes the sequence number in the reply as the acknowledgement number that was sent by the sender. That is, we see here 79. See this 79. So the acknowledgement sent by the sender in the packet is changed as sequence number. And it acknowledges for the packet number 43. And what does it mean? It means that I have received the sequence number 42 and I am expecting the next packet as 43. That's why then the host sends 43 here. So see this here, 42, 40. Sequence number is sent, let's say 79, it sends back the next one as it. Now the question is how to set this TCP timeout. If you remember, if you go back a bit, we had seen a TCP timeout here between sender and receiver. So how do we set this TCP timeout? How do we keep this in mind? The TCP timeout is kept in such a way that it should not premature before you get back the reply. What it means? It means that it should wait as much of time as it thinks that packet would take, keeping in mind the maximum amount of time it should take. Also, it should keep in mind that maybe there are some delays that a packet faces while it is sent from sender to receiver. Also, some delays that would take that would be taken by the receiver in processing of this packet. And also keep in mind that there will be some delays which may be faced by the acknowledgement while it's sent from the receiver back to the sender. So premature should not be that short. And premature and TCP timeout should not be that large also, that you keep on only waiting and waiting and waiting till there is no acknowledgement comes. Packet has already been lost, but you're still waiting for it. That wastes the time. So we would require that timeout is set. It's an important thing. Keep this in mind. How do you set up this timeout? You set up this timeout in such a way so that it's not too long that, you are waiting for the acknowledgement, nothing is coming, packet is lost or acknowledgement is lost, but you are waiting. It wastes a lot of time. And it should not be too short that you do premature timeout, and then after that the acknowledgement comes, but you had already sent the packet again, so you had done unnecessary retransmissions. So you need to set up the TCP round trip times in such a way that it is the best one. Is an examples of the same thing that has been given. So what did we get as of now? Let me go back. So what do we get from this TCP protocol that we just now understood? We understood certain points in TCP in today's lecture. The first one is it is reliable. How did we get this reliability? We got the reliability because we sent a packet and we confirmed whether packet was received or not. The second one was it was ordered. We sent a first packet, we received the acknowledgement first packet, then we sent the next acknowledgement, then we third and acknowledgement. So we went in order of 1, 2, 3, 4. And also in the header, there was one of the field which is checksum. Not just that packet is received and confirmed I have received it. Like I was planning to send a file to Ramanand. So now I have sent the file to Ramanand. Ramanand received it. Everything was done perfectly. First three-way handshake, then transfer, then acknowledgements. And Ramanand said, yes, sir, I have received the file. I confirm, okay, this is the end of the data transmission. Fine. So Ramanand received it. It was reliable data transfer. But was the file that was received by him completely received, as in the case, maybe there were some errors within the file. The packet was received, the segment was received, but with errors. So we have a mechanism for it, which is error checking. So we have error checked delivery here. How? We have internet checksum that would take care of the errors, that would see whether the data has been received correctly or not. Let's see an example of TCP. Where do you see this TCP? Well, most of the important communications that require reliable delivery, correction oriented services work on TCP. Typically www, the World Wide Web, email services that you use, remote administration like Telnet. It is Telnet, what we'll mention it as a remote administration. This is based on TCP. File transfer, FTP, and so on. They are all based on TCP. So TCP solves our problem of lost packets also, duplicate packets also, out of delivery packets also. And also TCP helps us in minimizing network congestion. We'll see flow control to understand this. TCP has its own level of abstraction. It covers the underlying network delays. Doesn't care about what network layer, sender doesn't care what network layer and others does, because TCP, or let's say transport layer protocol, does the abstraction of underlying network delays. And TCP is optimized for accurate delivery rather than timely delivery. So if we have TCP, it's accurate as compared to UDP. If it's UDP, we say timely. Here we do not, in TCP, we do not emphasize on timely delivery. We say let it take time, but I want to ensure it is error free and I have a complete file. But UDP says no, even if there are some issues with it, even if there are some packet losses, send me on time. I want it on time. It Mhm. Right. So I would want you to go and understand completely the segment structure here that we have discussed today. Okay. Let me go back. I want you to go ahead and understand this very well. Well, source port number, destination port number, we understood this. We understood the data below. So whatever is left in between, starting from sequence numbers, starting from flags and so on. Okay. As an example here, there are flags here as sync, fin, and RST. Keep this in mind. If the sync flag is set, what I mean by set means if S here, let me annotate it. If S here, okay, is set, means it is 1. This is the initial sequence number. The sequence number of the actual first data byte and the acknowledgement number in the corresponding acknowledgement are then this sequence number plus 1. That's how it will go ahead. Now, if this sequence flag is clear, not set, means 0, then we say this is an accumulated sequence number of the first data byte of the segment, typically for this current session. Likewise, we have acknowledgement here. Here. And what is this? Acknowledgement number. We have a 32-bit acknowledgement number above this A. If the acknowledgement flag is set, this ACK or this A is set, then the value of this field is the next sequence number that the sender of the acknowledgement is expecting. So acknowledgement number's value would be, I'm talking about this. The value of this would be the next sequence number that the sender is expecting. That's why I said you go back, revise this. I want you to understand this so that it is easier for me to go ahead with the flow control. Header length, I already mentioned what it is. You can call it as data offset also. It's a 4-bit size. And what is its purpose? Its purpose is to give the size of the TCP header. It will give in a 32-bit word. The minimum size of the header here is 5 words. The maximum size is 15 words, which in other words means the minimum size that we will have of this header, that is the TCP header, minimum is 20 bytes, which is 5 words. And the maximum that we have here is 60 bytes, which corresponds to the 15 words. Alright. So 60 bytes is the maximum size that we have. Now, if we have 60 bytes here, what was the 40 bytes we used it for? This won't change. This remains the same. The size here same. All this remains same, except one thing. That is what? Options. That is variable length. This means that, in other words, options field here can have a size of how much? 40 bytes. Plus the 20 of the remaining here makes it as a maximum of 60 bytes. But typically, if question is answered, what is the size of TCP header? Keep in mind it is kept to be 20. Okay. And what is the size of UDP header? It is 8 bytes. Another thing that is somewhere here is not used. There's a difference between options and not used. Option is basically If you want to negotiate between sender and receiver on certain protocol, like certain things like maximum segment size, okay, or there is some other protocol that between sender and receiver you want to negotiate, you can use options field. But not used has been kept empty, and it has been kept for future use. In case you want to set some other flags, newer things come in TCP, then this reserved 3 bits can be used. The bits here, the 9 flag bits that we have here, they are known as control bits. 1, 2, 3, 4, 5, 6, 7, 8, and 9 here. These are known as control bits, the flag bits, the 9 control bits, which include urgent, ACK acknowledgement, PSH as push function, RST as reset the connection, SYN as synchronized sequence number, FIN, that is the last packet from the sender. When it's set, means that I am going to end, this is my last one. The window size, the receive window, we'll study this when we'll go for flow control, and we'll also study it in window scaling. The checksum you already studied in the previous one. Just a revision of it. Checksum is a 16-bit field, and we use it for error checking of the header and the payload, and pseudo header as well. And what is a pseudo header? Some books might mention here that error checking is to be done on the header here, that is mentioned here. This on the payload, that is this application data, and a pseudo header. What is a pseudo header? A pseudo header consists of source IP address, means network layer, the destination IP address, the protocol number for the TCP protocol, that is 0x0006, and the length of the TCP header, including the payload, that is in bytes. So to do a proper checksumming, a pseudo header is to be included. Why we call as pseudo header? Because pseudo is because it's not actually part of the TCP, it is part of the IP header. The source IP address, the destination IP address, the protocol number that we had, the glue between the two protocol, these two layers, these constitute a pseudo header. And to do a proper checksumming, we should have pseudo header included with payload as well as header of TCP. What are these pseudo headers? These are some of the important parts of IP headers that we require. That's why checksumming is done on this. I hope this is clear. Any questions? Ramanand? Any questions? Okay. There is the last part before I actually go on. There is some part which is known as padding as well. And what is that? A TCP header uses padding to ensure let me just clear it up. I hope you understood all these, what we have here. So before actually I say what padding here is, let me take the options field. We saw that options is of variable length. Okay, now variable from 0 to 320 bits. Typically, since it's a 32-bit size, so it should be divisible by 32. The length of this field is determined by the data offset field. There are different options that come across. We call it as option kind. 1 byte, option length 1 byte, option data, it's of variable field. These are the parts that can come within this option field. There will be like a flag, and the first flag being option kind, the second being option length, and the third one is option data, that's of variable length. The first one that I mentioned, option kind field, this indicates the type of option that you're going to use. If you're using among the options, this is the only field that is not optional. All right. Let me repeat. The first field in the options is option kind, OPTION dash kind, which is of 1 byte. And what is the purpose of this option kind here? Option kind indicates what type of option are you using, and this is the only field that is not optional. Now, depending upon what kind of option you are dealing with, the next two fields may be set. The next field comes here. We call it as option length. Okay, what is option length? It indicates the total length of the option field. And the rest here is the third one, that is option data. That would contain the data, the actual data that option is supposed to say. Maximum segment length is how much, put that in the data. This would be applicable only if you want options. Among this, only the first option is to be kept, which is not optional. Okay, this is fine, optional field. The next thing that comes after option, you see here, it is data, but actually it is not so. There is something which comes between data and option, which I have drawn here in red. And what is this? This is known as padding, PADDING. So the TCP header padding is used to ensure that the TCP header ends and the data begins. So it's a 32-bit boundary that will come across here, which says that header is finished. Now after this, what is coming? The data is supposed to come. And what is within padding? What is the padding composed of? The padding here, I'll write here, PADDING. So what is this padding? It's a boundary. What is the boundary between? It's a boundary between two things, the header part and the data part. It separates the two. It's a 32-bit boundary, and what is the value of this? It's zeros, all zeros. And what would the receiver understand with this padding? It would understand that these 32 bits indicate the end of the header part, and whatever I am getting after it is basically the data. This is the actual data that's supposed to receive. Okay, Ramanand, I think I'll stop here. All right, is there any question? Everybody? Any question? I think there was problem from your end that you didn't have voice. I saw your message late. For us, for Ramanand, it was working fine, so I believe others would have as well. Ramanand, you're taking attendance regularly. Good job. It's fine. Send me and keep taking attendance as well regularly. And by now you would understand attendance really helps, right, Ramanand? Okay. All right. Another thing is the assignment. So I have given the third assignment. The last date supposed to be Ramanand when? Okay, day after tomorrow, is it? 4th. Okay, 5th June. Nawazish, okay, fine. It's 5th June. So this week I won't give any assignment. Next week I'll give assignment. Once we have 5 assignments, I'll stop. We'll keep a target of 5 assignments. Alright, keep in mind assignments are all covered within our syllabus, including if I send some extra videos for you to learn from. Let it be 5th June, that is fine. I have given email addresses. Please send to the specific email addresses that I have sent so that there is no confusion. Okay? By weeks or next week's time, I'll send a confirmation of the email, the assignments that I have received. All right? Okay then. I'll see you in the next class. Bye-bye.